Hello and welcome back to Calculus 2, section 8.5. We're talking about ratio test, root test, and two comparison tests, direct comparison and limit comparison. Now, we start with a ratio test, which is a very interesting test. And this test will be actually used again in chapter 9. So, ratio test says we have we have summation of some kind of an, whatever, starts somewhere, goes to infinity. Can start at 0, 1, whatever is allowed. So we have a series, and that series will converge or diverge by ratio test this way. You find the limit of the absolute value of an plus 1 divided by an as n goes to infinity. And you can have three cases from there. One case is that this is less than 1, in which case you have convergence. Or you can have larger than 1, in which case you have divergence. Or you can have equal to 1, inconclusive. So this is what you have to memorize. The test is this part over here, put on a cloud. That's the test. You have three possibilities once you compute that limit. Summation 1 to infinity of, let's say, uh, 2 to the n divided by n plus 1. So we look at this one. We say, all right, an is 2 to the n over n plus 1. Then an plus 1 must be 2 to the n plus 1 over n plus 2. Because n is replaced by n plus 1, and then you have plus 1, so it's a plus 2. To do the ratio test, we find the limit as n goes to infinity of absolute value. Guys, this absolute value is not there for decoration. You have to have that absolute value. That will be further reinforced in chapter 9. So limit n goes to infinity, 2n plus 1 over n plus 2 divided by 2 to the n over n plus 1, close absolute value, and now we need to work on this. Well, we have division of two fractions, so we know that we are supposed to flip and multiply. Flip and multiply. And now, the way to solve this limit would be to cancel as much as possible. Now, we're going to use the trick over here to separate this plus 1, so that's going to be 2 times 2 to the n over n plus 2 times n plus 1 over 2 to the n. 2 to the n will cancel, and we are going to have the limit n goes to infinity of 2 times n plus 1 over n plus 2. in absolute values. Now, since your limit goes to infinity, and you have n over n, same exponent, it's the ratio of front coefficients. So the whole thing is equal to 2, which is larger than 1, which implies that the series AN is divergent. So, the answer? So, what do we get? Remember, we got this case. The limit was equal to 2. Since the limit was equal to 2, that's bigger than 1. Therefore, it falls into category of divergence. Are we all agreeing on that? So you do your limit with whatever witchcraft you know from Calculus 1. Whether it's basic limits from Chapter 2 or more advanced L'Hopital rule in Chapter 4. Whatever solves the limit, solves the limit. That's all Calculus 1. Calculus 2 is knowing what to do and what to set up, and also writing the answer. So what's the answer? The answer is series 2n over n plus 1 from 1 to infinity diverges by ratio test. That's the answer. Now that's where you get 2 points. And everything up is partial credit for 8. If this was a 10-point question. So one more time. You see the problem. You will eventually realize that when you have mixtures of different types of functions, like here you have exponential on top and polynomial on the bottom in the denominator. When you have mixture of different functions, most likely ratio test is the one that will take care of it. So what you have there is 2 to the n divided by n plus 1. So that is your sequence an. Then you create an plus 1, and then you use the test where you divide an plus 1 by an. You do a whole bunch of algebra, and eventually when you apply the limit, you have the answer 2, which is bigger than 1, and in our book that would be divergence. Let's take a look at another example. Summation, let's say 0 to infinity of n squared minus 3 divided by n factorial. You remember the factorials? Yes. So factorials would multiply all of the numbers up to the value of the factorial. So 5 factorial is 1 times 2 times 3 times 4 times 5. And then you can write this part as a 4 factorial and then times 5. So you can write 5 factorial as 4 factorial times 5. Or you can write it as 3 factorial times 20, right? Because you can peel off 2 terms or whatever. Anyway, it's a little snippet on factorials. We go and say an is equal to n squared minus 3 divided by n factorial, and an plus 1, which is the next term, is n plus 1 squared minus 3 divided by n plus 1 in parentheses factorial. And now we set up the limit. Limit n goes to infinity. Absolute value. Expand the an plus 1. We get n squared plus 2n and then minus 2, because you would have plus 1 and then minus 3. Divided by peel off the extra term, so n plus 1 times n factorial. So if n plus 1 is the next term, the term before that was n, the term before that one is n minus 1, n minus 2, and we already saw with the 5 that you can actually write all other factorials in a factorial time the last term. So we peeled off n plus 1. Maybe we can write that as a formula. Times n factorial over n squared minus 3. So the double fraction I immediately wrote as flipped multiplication to save some time, and I expanded everything so we are not writing this 15,000 times. I should note over here that n plus 1 factorial is n plus 1 times n factorial. This is something that you will use over and over and over again when you see factorials. And the meaning of this was, as I said earlier, 5 factorial can be written as 5 times 4 factorial. Because 4 factorial contains 1, 2, 3, 4, and then times 5 makes it 5 factorial. So you can peel off 1 or 2 or 3 or whatever amount of terms you want. Right? 5 factorial can also be written as 5 times 4 times 3 factorial. Because 3 factorial will contain everything down to 1, and then you have 4 and 5, so it creates 5 factorial. So you have to multiply all of the integers all the way back to 1. All right, so now when I set up this limit and goes to infinity, we see that this cancels, and you are left with n squared plus 2n minus 2 divided by n plus 1 n squared minus 3. Now, depending on your prep for this class and knowledge from Calc 1, you might immediately see that this is equal to 0 because the exponent in the denominator is higher than the exponent in the numerator. And when we have that, as n goes to infinity, we have 0. Or you don't know that, in which case the L'Hopital rule, and then grind it and get the 0 eventually. So now that's less than 1, which means that our sum an converges. I will write the answer. Summation of n squared minus 3 over n factorial from 0 to infinity converges by ratio test. And that's the answer. You can see again, we had the combination of 2 different functions. We have a polynomial in the numerator, and we have a factorial in the denominator. Are you migrating south? Answer real quick. There you go. That was real quick. You want to do it real quick. You guys know that you can close those windows, right? Yeah, I know. It's amazing that it's November. You guys have windows open and the air conditioning down on -70.
Oh, that was you? Yeah, it was me.
I don't care. It's just most of you are sitting in jackets.
It was just really hot when muggy in this room.
Ready for the next one? One more example? You know how we confirmed that harmonic series diverges? Let's check it out. From 1 to infinity. So an is 1 over n, and an plus 1 is 1 over n plus 1. So now the limit n goes to infinity of 1 over n plus 1 times n over 1, right? That's plus times. And what's the limit? What's the limit? 1. Which means test is inconclusive. We know it diverges. We can do p-series. We can do integral test. But we see that this divergent series, you can detect divergence by divergence test, right? Because that was inconclusive. And here's ratio test being inconclusive as well, right? So you can't use every technique on every problem. Just like you can't use every integration technique on every integral. So it's time for you guys to start classifying these. You already classified before the derivative. And you look at the derivative and you say, this is product rule, this is quotient rule, this is chain rule, this is implicit differentiation. Because over time, you got used to the form of the function and which rule is to be used. Then you moved to integrals and did the same thing. Oh, this is by parts. This is partial fraction. This is trig sub, if you don't see the u sub, right? So, I know. So you classify integrals. And you know the form, and then you know the technique. It is time now to start classifying series. And this is where the sheet that I gave you comes in place. You see that the nth term test, also known as divergence, is the first on the list. You should try that first thing when you see any series. If that one comes out as inconclusive, which means limit is equal to 0, that means it's inconclusive, then it's something else from the list. You have other 9 options. Observe that geometric series has exponential form. So, here's your classification. If you are only seeing exponential form, like 3 to the n, 1/3 to the n, or something like that, well, it's geometric series. There's your classification. If you see subtraction between two terms that look pretty much the same, or you have something that you can use partial fractions, that's going to be telescoping. If you subtract two sequences within a series, it's going to be telescoping series. You are classifying further. If you just see a polynomial looking term, n to some power, that's p-series. If you see something that you can integrate, now this is bringing in, you know, all the integration techniques, it might be integral test if it fulfills those 3 conditions. So see, there is a clear classification, what's used where. It's not a guess. And it's not, let me try all 10 on the first problem, then try all 10 on the second problem, because that might take some time. Further classification here is what we just did. And ratio test is absolutely amazing when you have different types of functions mixed in together. This is 1 over n harmonic, so not that special, but over here you have a polynomial n factorial, and over here you have exponential n polynomial. So when you mix different types, this ratio test stands out. So let's try another. So one more ratio example, something from homework. And then we're going to jump to the next one, which is root. So I have to flip all the way to, there we go. Under basic skills, they're asking you to compute problem 13 is interesting. A lot of these are interesting, but summation k e to the negative k from 1 to infinity. Go. I'm going to write the first step, and that is to rewrite the series as k divided by e to the k, because it's easier to deal with stuff that way. It's just algebra step. What happened?
I got E at first, so I had diverges, and then I switched my answer to 1 over E because I figured out what I did wrong, but I still kept it as diverge.
Yeah.
So now it's 8 then?
Well, yeah, counter is either n or k or m, or you can have whatever, right? Like your variables could be x or t. Right? Yes, now it's 8.
That's good. Used. Now, what is that right there? That E to the what? On the right, top right?
This?
Yeah.
Clearly k plus 1.
K plus 1. Everything's fine. Let's go with those. Let's go with those. You get those? I'm normal. You got it already? You what?
I said if I did my multiplication, I would.
Your multiplication? What's wrong with multiplication?
I didn't multiply right on the last
Oh.
limit. Oh, I didn't switch the E and the K when you cross multiply or when you multiply.
All right. The next test is the root test. And the root test looks very similar. We have summation of nth root. Sorry. We have a summation of an raised to exponent n. From 0 to infinity or 1 to infinity. I'm just going to put it like this. So now you will apply the limit as n goes to infinity of nth root an to the n, which is technically just the limit n goes to infinity of an in this case. Which again has 3 less than 1, converges, more than 1, diverges, equal to 1, inconclusive. On a cloud. So earlier you took the limit of n plus 1 over an in absolute values. Now you will have some sequence raised to the nth power. Now we'll get creative with that n eventually, right? But the main idea is you hit that just with the nth root, and then we'll cancel. You just have an there, and then the limit, right? Yes.
The table doesn't have and to begin.
Because the table is in a different book, but this is easier to understand. So yeah, you just take the nth root. That's the method.
But if you have like this, the nth root and raised to the n, don't they just cancel out?
Yes, that's why the next step doesn't have either of them.
Oh.
There we go. Just look a little bit to the right. All right. All good. Let's not mention it. Let's take a look at two examples. Two examples should be sufficient, I guess. Let's start with 19 because it's so busy and so easy. K goes from 1 to infinity, and we have 10k cubed plus k divided by 9k cubed plus k plus 1, everything raised to the kth power. So we know that we are supposed to take since the book uses k's, I learned it as n's, so I like n's, but the book uses k's, so whatever. We take kth root of the sequence there. So when you take kth root, it will kill the exponent k. So we are just working with the limit of 10k cubed plus k divided by 9k cubed plus k plus 1 as k goes to infinity. And you see that numerator and denominator have the same exponent, which means we take the ratio of front coefficients, which is 10 over 9, and that's larger than 1. We have divergence, and we will just write the answer quickly. Series from 1 to infinity of 10k cubed plus k divided by 9k cubed plus k plus 1 to the k diverges by root test. I'm done. So
how do you make that 10 over 9 again?
Exponents are the same. So you will, because it's polynomial divided by polynomial, you look at the front coefficients. Or you can do L'Hopital, derivative over derivative, it will be 30 over 27. And then you have to do it again and again, and when you cancel the fractions, they will go down to 10 over 9. What happened?
Nothing.
So that K basically cancels out.
In this example.
Right. So,
What happened?
alright.
If you tested them out, you get an exponent of calculus and value.
What?
What about the one?
This one?
Yes.
That one will be, well, there are two ways to compute this. One way to compute this, sorry, here. One way to compute this limit would be to use the shortcut method, which is if the exponents are the same, then it's front coefficients. If the top has the bigger exponent, it's infinity. If the bottom has the bigger exponent, is 0. So that's one way to memorize that. Yes? So the rules that you memorized in pre-calculus for asymptotes are the rules that take care of this limit. Where the exponent in the numerator is larger than the denominator, you have infinity. If the exponent in the denominator is larger, you have 0. And if they are the same, like in this case, it's front coefficients, which is 10 over 9. So that was the pre-calculus approach before we learned anything about limits. In Calculus 1, Chapter 2, you learn for limits at infinity that the way to solve these limits is to divide each one of these by k cubed, because that's the largest exponent. When you divide everywhere by k cubed, you get 10 over 9, and then you get 1 over k squared. Well, 1 over k squared goes to 0 as k goes to infinity. You will get over here 1 over k squared again, and over here you will get 1 over k cubed, which is also going to 0. So all terms go to 0 except the first ones where the k cubed canceled. So that's way 2 to solve this limit from Chapter 2, Calc 1. And then we have one more to worry about. If you want to solve it using L'Hopital's rule, you see this is infinity over infinity, which is indeterminate form, which means that you can take derivatives, independent derivatives, the numerator and denominator, and you can keep doing that until you run out of infinity over infinity, which actually would just leave you with 10 over 9 at that point. So there are 3 separate ways that you can do this particular limit. Next one, not that many choices. So we solve the limit, again, whatever Calc 1 witchcraft you know, use it to come up with the limit. Now the next problem says, how about 22? It says, summation 1 to infinity of 1 plus 3 over k to the k squared. Now, I hope you understand that the k squared is k times k.
Put that back. Maybe cancel it out.
So 1 will die, but 1 stays. So once you apply the limit, k goes to infinity, and you do the kth root of 1 plus 3 over k to the k squared, 1k dies, 1 stays, so you are left with 1 plus 3 over k to the k.
Good question.
Can do it again.
How do you know it's k to infinity every time for the one that? Is that just part of the rules?
Yeah, you're sending it to infinity.
Oh, I see. Alright, I got it.
So now the question is, what is the limit now? You can't do it again. You can use ln
ln on this.
to take the limit, sure. You can use ln. Or, anyone?
E.
E. It's e cubed. Yeah, there's a 3 right there. So it's e cubed. You see? So this is e cubed, which is bigger than 1. Divergence. Done. Now, this is where you should, you know enough mathematics to actually start wandering between different disciplines, parts, and start connecting the dots. Few of the formulas that you covered earlier, we said that the E, we said that in this course as well, if you go back to 6.8 or something, we said the definition limit n goes to infinity of 1 plus 1 over n raised to the n. That's E.
How did you...
And then, wouldn't make sense that if you have some exponent a, that a will show up in front of n over there, right? Because it would technically be this to the a, and then we see that then e to the a is the limit n goes to infinity of 1 plus 1 over n to the an. But then also we have a situation where you have e is equal to the limit n goes to infinity of 1 plus, I'll just put over n to the n, and now I'm going to use lowercase, let's say r. Well, that gives you e to the r. Now you can do all of these proofs using L'Hopital rule to show that all of these hold. So I can either have an exponent here, which is times n, which will show up as exponent on e, or I can have exponent here as r, and that would also show up as exponent on e. Now any of these, obviously, when you do the proofs, will show. Now, do you know something from pre-calculus where you actually seen this at work? And the answer is, hell yes. Remember your compounding formula for loans and stuff? Used to be that the amount is equal to the principal 1 plus r over n times nt. And then you had the continuous compounding, a equals PERT. Do you see that this portion here of 1 plus 1 over n to the n is e? You have the r in the exponent, which is in the exponent, and then you also have this extra t that is on the outside, which is behaving like the a on this case. So they're all there. These formulas don't fall out of nowhere. This is all this stuff. So this formula compounds, it's called continuous compounding. It compounds all the time and gives the maximum possible amount, where this one will always give less because you are compounding once a year, twice a year, once a week, once a month, right, and so on. That's this n. So n is 12 or 52 or something. So when you see within these limits, right, for our Calc2 now, when you see this type of a structure, or this type of a structure, you know it's e. And then you say either this one or there, but if I have extra stuff floating about, those will be the exponents of e. You can have both of them. Right, there could be 2k. So if this was 1 plus 3 over k raised to the 2k, you would actually have e to the 6th power, because 2 times 3 is 6. So that was a little bit on prerequisites from Calc 1. Another one? Yeah, why not? So summation 1 to infinity, k squared, 2 to the k in denominator. Go.
I'm lost. What What do I do? I have right now I have limit k to infinity. And then k squared over 2k. That's the first thing.
Oh, yeah.
I'm switching this to n. I hate that. N is so much easier to write. K is 2 strokes. N is 1. So, because I can.
No, that's not what I meant.
No. That's what you said. So when I apply the nth root, I will get limit. N goes to infinity, and what we have is n to the 2 over n divided by 2, right? We know that the nth root of x, let's say, is x to the 1 over n, right? That's like a square root is a half, cube root is a third, so nth root is 1 over n. And then you have 1 over n times 2, and we have 2 over n there. So we are supposed to consider the limit 1/2 limit n goes to infinity of n raised to the 2 over n. Yeah, what now? Yeah, it's infinity to 0. It's in the, yeah, it's just, yeah, right?
Can you do something to it?
Yes. Yes.
What would that something be?
That something is a move of the century. Look at this. Ready?
Oh wow.
See what happens when you apply that.
You get 1 over. Or you get 1 over 2. So
So this is one of the oldest tricks in a book. You see something crazy you don't want to deal with, you substitute that, right? It's like we go to a restaurant, you order chicken pepper, you say no pepper, put mushroom instead. You substitute, right? You could have ordered chicken mushroom, but I mean, why would you? Right? No, that actually happened when I used to work at a restaurant. many moons ago, and that's the moment where I realized that I cannot be server ever. I work as a busboy, and I heard someone say that, and I don't think I would be able to take that order. Chicken pepper, no pepper. Yet the menu has grilled chicken and chicken marsala and chicken this and chicken that, and there are 10 items on the menu. It was an Italian restaurant. 10 items on the menu had chicken. This person picked chicken pepper and said no pepper.
What if he has a special sauce?
Yeah, special sauce called mashed potatoes on the side. That's the special sauce right there. They had chicken prosciutto, chicken this, chicken that. Give it chicken pepper, no pepper.
Crashing. You want?
Have some more Skittles.
This is not for me, it's for study.
Oh.
So I listen to your videos.
Oh, that's why you're sleepy all the time. Let's try do the substitution. So I'll say t equals 1 over n. See if that helps. So it becomes 1/2. And now limit, if t is 1 over n, then n is 1 over t, which goes to infinity. And I have, again, 1 over t raised to 2t. Now, did this help at all? If 1 over t goes to infinity, then it's 1/2 limit t goes to 0. Right? That changes.
Yeah, you still get infinity to do.
Do I? And then I have 1 to the 2t is just 1 raised to the t to the 2t. We're just trying substitution to see if it helps.
I didn't see that. 0 to the 1. Or, yeah.
So did this help at all?
No. It's 0 to 0.
It's 0 to 0. What do we know from growth rate of functions? What kind of 0 to 0? 0 to the 0 could be what? Would you say anything to the 0 is what? Anything to the 0 is? 1. And 0 to anything is? 0. So now, when you look at these two, they are at odds. If you have A to B, right, and they both go to 0, so which one is it? Is it 0 or is it 1?
Both.
It's not both. It's 1. Exactly. It's 1. Growth rate of these functions is the same.
Why is the one take precedence?
Both of these growth of these functions is the same. This is a t and this is a t. So you see, 0 to A is going to give you 0. And then B to 0 is going to give you 1. If this and this grow at the same rate, that one wins.
I get that. I was asking 0 to 0. Why is it 1 and then 0?
I can say graph it or do the L'Hopital, right? If you do L'Hopital, you'll see it. But then we can actually trick this to be 0 or anything else by switching these functions here and here to be t squared or root t, or so we can have different combinations, and then when one is growing faster than the other, you might end up with other things. So this actually works out to be half, which is less than 0, and we have a convergence. There's the 1/2 in front, yes. So limit is 1 times 1/2 is convergent. Yay. Yes.
Why do you show the limit from t 1 over t to the infinity t to 0?
It's easier. Well, you can't really work with this, right?
Could you just press this n square root of n square?
What do you mean n square?
The n to the 2 divided by n.
Mm-hmm.
And you just n square root of n squared. Like 1/3.
N to the square root of n square, like this?
It's like square n to the 1/2 is the square root of n, right?
Yes.
So you do the same thing with that.
But I don't have a half. It's a 2 over n. 2 over n is 2 times 1 over n. There's no half. Half would be 1 over 2n, and then a half gives you a square root. So we can rewrite it with a square root. I'll write it out. So if you have a term n to the 1 to the 2 over n, this is nth root of n squared. That's what it is.
No, you should have given the bottom end, no? N squared.
No, that would be if it was negative. Right? It's x to the negative a that gives you 1 over x to the a. X to the 1 over a gives you eighth root of x. I'll leave that there. All right, direct comparison. We got to the point when we are talking about comparison tests. If you look at your sheet, I place them, well, not I place them, I picked the sheet which actually places those on the bottom. Those are the last resort tests. You really don't want to use them right off the bat because they can be tricky. And direct comparison requires a proof. Limit comparison will require taking the limit. So for direct comparison, you are supposed to kind of guess the answer and then like have gut feeling of what should happen, and then pick a p-series which is of that form, and then do the proof that will establish the condition. And if that works out, then your gut feeling was right. If that doesn't work out, that means that you have to do something else. So the idea is that you are trying to solve convergence or divergence of some sequence an, which is not particularly friendly in terms of it's not telescoping, it's not geometric, it's not ratio, it's not root, it's not integral, right? Nothing that you have learned so far works on it. None of it. So you say, all right, I'm going to compare this to something that I know. But there has to be a condition, like your integral test has those 3 conditions, and then you can use the integral instead of the summation. Over here, you have a condition that you have to also prove, and if that condition works out, you're good. If it doesn't work out, you have to use something else. So now we can figure out what that condition is by observing a simple graph. So you have your n counter, you have your an over here, and now look at this. You have some crazy an over here that it's all over the place, right? So that's an. And then you figure out some kind of nicely behaving bn. Whose summation converges. And now we apply common sense. Since your an is squeezed in between 0 and bn, then the summation of an must also converge because summation of bn converged. Does this make any sense? So you have some chaotic an, and you are able to bound that with a different sequence whose series converges. So yeah, it's similar to squeeze theorem. That means that an, so I'll say if this holds, then summation an converges. And then another situation, so that's your condition right there. And another situation arises where again you have some chaotic an, and you are able to find nicely behaving, predictable bn whose summation diverges. So in this case, if 0 is less equal than bn less equal than an, now if that condition holds, that will mean that summation of an diverges as well. It doesn't really, look like much, but let's see. Summation of sine n over n squared plus 3. From, let's say, 1 to infinity. So good luck with that, right?
Yeah.
You can't take limit of sine n, because the limit of sine n is what? What's the limit of sine n in infinity? It's all of the values between -1 and 1, right? It's infinitely many values. There is no end to sine n at infinity, so you can say, oh, it's -1 or 1 or whatever. So you can't do this by using any of the limit stuff that we did. It's definitely not geometric. There's no partial fractions to do there, right? You have sine n in the numerator. So you can't use telescoping. It's definitely not exponential, so it's not geometric. So when you take a look at this problem, everything we learned so far fails on it. Now, what does your gut feeling say? Should this converge or diverge? Converge. Because this sine n is bounded by 1. Sine n can't go above 1. That should be clear. That must be clear to you. because you know that the range of sine function is 1, right? So the most this can be is 1. And this can go to infinity, right? So it seems like it takes the dive, right? But then you say, hold on. How about I consider Bn to be 1 over n squared? Because the sine can at most be 1, and denominator looks like n squared. You forget about the plus 3, right? In infinity, that really doesn't do anything. The plus 3, right? So you look at this and you say, well, I know that summation of 1 over n squared converges by p series, right? Because your p is 2, that's bigger than 1. So you say, if I am able to prove, what?
Do you ever take the limit of that? One of that?
No.
Oh, okay.
We're just going to compare this. So now, we are going to have convergence on this series if we are able to show this condition in red, that an is smaller, so need to show that an is smaller than bn for all n. So what do? We just simply write sine n over n squared plus 3 needs to be less, with a question mark, than 1 over n squared. Sine n is bounded by 1. So we replace sine n by 1. We cross multiply, and it holds. Answer. Since an is less than bn and summation of bn converges, series 1 to infinity sine n over n squared plus 3 converges by direct comparison. We compared the sequences and we have the condition fulfilled. Since everything worked out just fine, we have convergence. I will show the textbook graphs now. So these are the textbook graphs on page 644. The black series is the one you are considering. Nothing you learned so far will work with 1 over k squared plus 10. Nothing. Then you come up with a 1 over k squared. Technically, right, if you just ignore this plus 10 over here, you have 1 over k squared. So that's 1 over k squared. You know that one converges by p series. Right? I told you Monday to learn p series because we need it today. And now when you do math, right, comparison, direct comparison, you will see that this one is larger than that one, which means this one is squeezed, so it has to converge as well. On the other side, if you have 1 over square root of k minus 3, You take a look at 1 over root k. Again, see, just remove negative 3 from there. That one diverges because why? Why is this one divergent? 1 over root k. Why is it divergent? It is. What's p? 1/2. 1/2 is less than 1. Diverges. P less than 1 or equal to 1 diverges. P bigger than 1 converges. You have to memorize that. Guys, there's no escaping memorizing that sheet if you want to be whatever successful in this. Spend an hour, 2 hours, 5 hours, whatever it takes. Some people keep continuously writing it by hand to remember it. Without knowing every single one of those tests, it's going to be very tough because you learned product rule, you learned quotient rule, you learned implicit, you learned the chain rule, and you learned which problem, which function looks which way to apply appropriate derivative rule. Now you have 10 different rules. We call them tests. You can call them derivative rules. So now you have series tests. You have to learn the form, and you have to learn how to do each one. And that's the sheet. Now, you might be getting overwhelmed on that one because the whole thing is new. It's discrete mathematics. It is completely different type of thinking. It wasn't as, multiplication going into derivatives, going into integrals, which all looked pretty much the same. Now it's completely new stuff, but it's the same idea of you classify, see which one applies where, whole bunch of algebra, and in terms of calculus, just limits. That's all you do. Let's take a look at another problem for direct comparison. When direct comparison doesn't work, you use limit comparison with the same AN and BN that you tried for direct comparison. And even though I might say that most of the time it is limit comparison, so most of the people opt out, immediately do the limit rather than even messing and trying direct. Mark?
Why does it have to be smaller than n for all n?
You see the picture? The black sequence is smaller than red sequence. And the summation of the black series over there, so summation of the black sequence, which is the series, converges, and the red one converges as well. But because the red one is higher and red one converges, black one is forced to converge because it's squeezed. That's why AN needs to be smaller than what you picked, which is BN, which is red. You pick red, black is given in the graph that it's on the board. So red is what you picked, and you picked the convergent one. Now, the first time I saw this, I said, oh yeah, you just always pick the convergent one and we're good, right? But the condition on the proof is not going to work out if the things... So this is not stacking the deck. You go and say, I want this to diverge. You pick something divergent and it diverges. No. Your gut feeling says this diverges. You pick the divergent one, and if the condition holds, then, right, when you do the proof, when you do this part, right, when you do this part here, if the condition holds, then your gut feeling and your intuition and everything else worked out. Let's take a look at another example. From homework. So say, oh, it's not going to work. Let's try with 36. Most of these are actually limit there, so if it doesn't work, we'll just switch to limit. Summation 1 to infinity, changing all case to n's because it's easier to write, n square root of n plus 2. All right. This analysis that I'm going to do now is crucial, guys. Look at the board, forget about writing. Look at the board. I see n over here. That's n to the first power. I see square root of n here, which is n to the 1/2 power. Together, they are n to the 3/2 power when I distribute. I'm completely ignoring plus 2. So one more time. I look at the problem. I get 1 as exponent from here. I get half of the exponent from there. And I get 3/2 as the exponent. If I have 3/2 exponent, that spells convergence in a p-series world. All right? Oops. Spells convergence in p-series world. So what I'm going to do is I'm going to immediately put my bn to be 1 over n to the 3/2, and I know that the summation for 1 over n to the 3/2 converges by p-series. So I didn't just pull this n to the 3/2 out of nowhere. I said this part n gives me exponent 1 because n to the first power. This n over here is raised to the 1/2 power because of the square root. I completely ignored plus 2 because that plus 2, when you plug in infinity, you can't plug in infinity into it, so don't worry about it. So I got 1 plus 1/2 is 3/2, and then 3/2 in a p-series is convergent, so I am picking bn to be 1 over 3/2, and series as it goes to infinity, right, 1 to infinity, converges. So now that I'm done with that analysis, I have bn, and all I need to show now that an is smaller than bn. Because remember, bn needs to be bigger. If bn is bigger and converges, it forces the smaller one to converge as well. So I show that 1 over n square root of n plus 2 is smaller, with a question mark there, 1 over n to the 3/2. Is this the case? Unfortunately, no, right? But we tried. So now you have n to the 3/2 less or equal than n square root of n plus 2. If you divide both sides by n, which is okay because n is not supposed to be 0 and we start n at 1, we have the square root of n smaller than square root of n plus 2. Is this true? Yes. This is true. We have the answer, finally. Since an is smaller than bn, smaller or equal, and, very important, summation of bn converges, series, and now you can write it out, summation 1 to infinity of 1 over n root n plus 2 converges by direct comparison. And that's your answer. So one more time, I'm not making up stuff out of nowhere. Exponent on n is 1, exponent on this n is a half, because they're multiplied, 1 plus half is 3/2. Let me use 3/2. And that's the end of the story. Now I'm going to show the limit comparison test. And then we'll use it when we have to. Oh, we're frozen over there? Yeah, when the projector freezes, this is the time you switch to your computers and you watch the stream. While I mean, it might catch. Let me reboot the connection. There we go. I hope. Nice. Limit comparison test. So we have the same thing, right? Consider summation AN, pick BN, then you will have that summation BN to converge or summation BN to diverge, depending on what BN you picked, right? If you pick 1 over square root of n, then the P series, it diverges. If you pick 1 over n squared, by P series it converges, and so on. So depending on what you pick, you can pick harmonic 1 over n. Sometime you will have to do that. So you consider AN, you look at the AN, you pick BN, and you saw how I considered that, right? This was AN, and I analyzed AN, and I came up with 3/2. So that's why I say consider the series, and then pick BN. Once you pick that BN, limit comparison says limit n goes to infinity of AN over BN can be one of the two things. It could be L, which is finite, or infinity. So now we have cases here. Number 1, if 0 less than L less than infinity, then summation AN and summation BN both do the same thing. This is not mathematically what I should say. Then they both converge or they both diverge. We've seen this before with the integral test, right? If the integral diverges, series diverges. If the integral converges, series converges if those 3 conditions are satisfied. Your condition here for both of them to do the same thing, in this case, summation of AN and summation of BN, you need to get a finite limit. If you have a finite limit that is between 0 and infinity, then both will do the same. And then 2 lesser conditions that are still, I mean, they're not lesser, they're just less frequent. So if L is equal to 0 and summation BK converges, then summation AN converges. And if L is equal to infinity and summation BK diverges, then summation AN diverges. These are extra conditions. Uh, 99% of the time you will be dealing with number 1. Let's take a look at the simplest possible example we can. Summation 1 over k squared minus 3. From 1 to infinity. You know what I'm going to do first? Direct comparison. Don't we see that this is 1 over k squared? Right? We see that right off the bat. And what do we know about 1 over k squared in a series? It converges by p series, right? So we are expecting this series to converge. So we choose Bn 1 over, I put k again, n. I don't like the k because it's, look, k you have to do, right? N, boom, done, right? It's much faster to write, easier to write, so I like n better. I mean, plus my name, right? Can't pass it out. You can use whatever your name is, use that as your account. Have D's. Right? And M. M is a good one. M. Right? Also M. We have a D row, an M row, and then what was the J? Oh, so M, S O M J. But you gotta join them. J, you move somewhere else. Yes. Summation of 1 over n squared converges by p series. You can also do the integral test if you like, pain. And now we are expecting this to converge. Now I'm going to try direct comparison. Because I can, right? I need to show that an is smaller than bn for all n. So an is 1 over n squared minus 3, and I need to show that's smaller than 1 over n squared. Now look what happens when you cross multiply. See how hell breaks loose? You subtract n squared on both sides, and you get 0 less than negative 3. Right? So condition didn't hold. Now that doesn't mean that you are wrong and then this thing diverges. It just means that the direct comparison didn't work. Your gut feeling that this converges and that it needs to be compared to 1 over n squared is correct. It's just that the method didn't work out. So we picked the right stuff. 1 over n squared. We know that that converges. We know that we are looking for convergence. You try the direct comparison, didn't work. Now, put these two, an and bn, into the limit. Do the limit comparison test. You are going to get 1. Right? And the first line in our limit comparison test said that if you get a finite limit, any number between 0 and infinity, both sum of bn and sum of an will do the same thing. They both converge, they both diverge. Since summation of bn converged, then summation of an has to converge. And you proved the problem. So, placing the red x over here means that the method failed. Not that the problem diverges. That is one of the very common mistakes, guys. Oh, if it doesn't converge, then it diverges. No, 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 no. Method failed. Do something else. What's the else thing? Do the limit comp test instead. Right? So, what do? We go and say limit n goes to infinity of an, which was 1 over n squared minus 3, divided by the limit of 1 over n squared. Solve the double fraction there. That's going to give you n squared over n squared minus 3, and that limit is 1. You have a polynomial divided by polynomial. They're both squares. Take their front coefficients. 1 over 1. Limit is 1. This is that L. Finite. And if it's finite, what do we have here on the first line? Which I told you it's most of the time is this one. If you get limit to be 1 or 7 or e or whatever, then both do the same thing. So what's the answer? We gotta write that sentence. Converges. Since limit of an over bn as n goes to infinity is finite, and summation of bn converges, series summation 1 over n squared minus 3 converges by limit comparison test. The class ends at 8:50 or 9:50? 8:50, okay. Now it's 7:50, so we have one more example, and then we're taking the break. After the break, short section on alternating series, and we're done with the chapter. So we accomplished 5 tests today. Yeah?
Should I be nervous?
So don't worry about it. We'll have power series coming up. It's gonna wake you up. It's gonna be epic, I promise.
I'll see it. I'll be able to
Move in, yes, with the sleeping bag and everything.
Yeah. I'm sure.
Next example, 32, summation, 1 to infinity, change all k's to n's, n over, I know, n cubed plus 1. What is Bn? Immediately. What is Bn?
Well, the denominator is crazy.
And put the one over 2 to write about and put the other.
What the heck, dude?
No, that was actually correct, but now simplify the algebra. What is the Bn in the simplest possible form? I need you to be able to do the basic algebra in your life to survive these sections and chapters. What is Bn? And you just stare at this. What is the part that we ignore? We ignore plus 1. Okay, fine. So what's left? 1 over n squared. And then what else you have? So? Would you like to be dramatic? Yeah. Yeah, n to the negative 1, right? 1 over n.
How'd you get that?
How I get that? Observe. That's how I got it. Easy. So I have n over n cubed square root. You cancel n's into 1 over n squared. Square root of 1 is 1, square root of n squared is n. Boom.
Wow.
This is harmonic. So summation 1 over n diverges. Pick your reason. Integral, P series, harmonic. You can write any of the 3.
We only have to simplify the expression.
Mm-hmm. That's the algebra behind it. So I'm going to actually do that in blue. Square root of n over n cubed, which is 1 over n squared with the root, which is 1 over n, and that's what we have up there. Good. We are looking for divergence, right? If we are looking for divergence, we need Bn to be smaller than An for direct comparison. Direct comparison need to show Bn less than An for all n. Okay, that's 1 over n needs to be smaller, you put a question mark, than the square root of n over n cubed plus 1. Fine. Square both sides. 1 over n squared needs to be smaller than n over n cubed plus 1. Cross multiply. N cubed plus 1 needs to be smaller or equal than n cubed. Take away n cubed on both sides by subtraction, and you get 1 less than 0. Fails. Test fails. Method fails. This is very important to understand, that if you don't get it your way, method failed. It's not going to be convergence because it failed here. You'll try the limit. If the limit fails as well, then you might have some issue with your thinking and setup and these kind of things. So direct comparison failed. Switch to limit comparison. As I said, most of the students choose to do limit comparison immediately, because most of the time limit comparison solves the problem, right? So we do the limit of AK divided by BK. I mean AN divided by BN, whatever. AN was this wonderful square root of n over n cubed plus 1, 2, plus 1, divided by 1 over n. All right, ready for some advanced algebra in your life? Square root of n over n cubed plus 1 times n over 1. Now we ship this inside the square root, and what does it do? It picks up square. So limit n goes to infinity. We have n over n cubed plus 1 times n squared over 1. So now that's when it goes under the square root, it picks up the square. You see that if you take it out of square root, it will become n over 1. This is what you would call next level, right? Next level algebra. And we have the square root of n cubed over n cubed plus 1. Now, the next one is the property of limits from Calc 1. The property of the limit said that if you have the limit of a function to some exponent, you can do the limit of the function and then apply exponent to everything. That is the property from Calculus 1 in chapter 2. You can go and find it. It's a theorem. So this means that I can actually do the square root of limit n goes to infinity of n cubed over n cubed plus 1. Which gives us square root of 1, which is L, finite. Which means both do the same thing. So now I get to write the answer. Since limit, I don't need to spell limit. Since limit n goes to infinity of an over bn is finite, and summation bn diverges series summation square root of k n over n plus n squared plus n cubed plus 1 diverges by limit comparison test. Yay. So first few examples worked with the direct comparison, and I really worked hard to find them. Most of the problems will be on your on the limit comparison side. So as I said, some of you opt out to on the exam to immediately try limit comparison without even trying to do the little proof over there. But those proofs are extremely easy, right? And some might argue that it's easier to solve inequality than it's to do the whole limit. Remember that limit can go into L'Hopital and it can go into all of these esoteric situations where you have to maybe use U sub or, right, what we tried in the other example and so on. So direct comparison, you know, textbook example, direct comparison should be faster to do, but again, it works on a much smaller sample of problems that you will encounter. So practice limit. I mean, limit is going to take care of 80–90% of your problems, and then some others you might. So you might want to switch maybe even. But there are cases when limit doesn't work. And you have to be careful about that, right? Direct will work and limit will not. And you will probably run into those as you do the problems. Before I close out this lecture, it's time for advice on passing next exam. The homework in a textbook is displayed in the standard format, where you have 10 problems for ratio, 10 problems for root, 10 problems for comparison tests. This is the homework in 8.5. Look at the title or heading for problems 40 to 69. Choose your test. This is what the exam looks like. Didn't the previous exam just say integrate? I didn't say integrate by partial fraction decomposition, integrate by substitution or whatever. Integrate, dot. What is the next test going to have, right? Now, what are the tests that we're going to use here, right? So this is where you practice. This is where you sit with that sheet and you go and you compare. This is what I see on the sheet. This is what I see in the problem. Okay, so here is some analysis over here. Problem 41. Everything raised to the k. Hey, root test. Problem 42. Everything raised to the k. Hey, root test. Next problem. Factorial. Ratio. Factorial. That's the only test that deals with factorials. You see factorial, ratio, right? This is how you classify your problems. And the only way you are going to learn that on this new setup that you haven't dealt with, discrete math, is to spend hours staring at these problems 40 through 69. Choose your test. The only one that is missing is alternating series, which is now next section after the break. But alternating series, you spot them like this, because all alternating series have -1 to the n. There is, if you look at your sheet, you should see summation -1 to the n times an. So that is clear. I mean, you just look at it and you immediately know. So alternating series are apart from everything else, because alternating series, right? And then obviously if you have a factorial, right, it's a ratio test. But then again, polynomial, exponential combination, or anything else, that it's different kind of functions would do it. Root test, root test. Okay, 48. Let's practice on 48 real quick. It says 1 over 5k minus 1. What test? What happened? Comparison to what?
1 over 5k.
And what's 1 over 5k?
1 over 5k.
Yes. What is 1 over 5k?
5K.
Yeah, what is it? What kind of test? What kind of function? What kind
So we just did.
No?
No, so we just did. Right?
P series is k to the 5.
Oh.
And this is 5 to the k.
Root
No?
ratio.
Well, it could be root. Geometric. It's exponential.
Oh, geometric.
So you are comparing this to the geometric 5 to the, right? Negative k. So R is 1/5, it converges, you are expecting convergence. And then you crank either direct, if that doesn't work, and it will not because it's minus, you go and it's limit comparison to the geometric series converges. Yeah, I had no clue what I was doing when I was taking this as a student. Right now, I just take a look at it and just. But you know what's the difference with me being a student and teaching it now? That sheet, you can shake me out of bed at, I don't know, 3 a.m. I will write out the whole sheet, and then I go back to sleep, right? So, what happened? Oh no, not the number, because there is the part that you missed. After I answer, there's his part, and then I go back to sleep. Yeah. So the only difference between that time, where I looked at this and I say, what's going on here, and now, I don't think that I'm any better in algebra now than when I was taking the Calc2. Because I worked as a tutor. My algebra was top-notch. Every day I worked on algebra with students. So I never had issue with that. The difference was, I didn't know that sheet. So all of this stuff will do you. Right now, 1 over 5 to the k, that's the geometric series. I have -1. That introduces the comparison, because that -1 is not there on the sheet if you look at the geometric series line. So that -1 on the bottom is forcing to do the comparison to the geometric series, and then whether it's direct or limit, most likely limit, definitely limit, because -1, if it was +1, you can do direct. And yeah, so 40 through 69, here's a whole bunch of other stuff. So yeah, 55, hey, right? Yeah, I know, it goes like this. A ratio, I mean, like nothing. Root, comparison. I just look at it. Oh, let's look at that. K over 1 over k at 3, P series. Comparison to this, right? By the limit, and you're done. You can do direct as well.
For 67, 68, 69, you have to come up with the AM ourselves.
Oh, yes. 67, 68, 69. You come up with a summation first. And then you did, look at this k raised to the ln k. Yeah, good luck. It's amazing, man. Look at 64. Sine squared of 1 over k. I know. We're gonna love that one. Tangent of 1 over k. So, how about 54? 5 ln k over k.
That's ratio.
5 ln k over k.
Oh, integral.
Integral. Right? Isn't that ln x over x and then u sub, and you have a du 1 over x and just right? Like this. But again, you have to sit down and don't waste your time working on these problems if you don't know the sheet, because obviously it's not going to go well. So learn the sheet, learn the methods and techniques, and then apply it. We will restart. So take a few minutes off. Restart the stream for 8.6.